Thanks, Tobias. Well, it's great to be back. I remember last time I was here, Dave gave me nearly a heart attack when he showed that the thallium fluoride cycling didn't work as well as he thought. And since the molecule I want to study is very similar, we had a lot of discussions since then, and I'm really glad that I can be back and actually show you that it works actually quite well for aluminum monofluoride. It's actually very similar. So my name is Stefan Truppe. I recently moved to a new position at Imperial. Last 5 years I've been building up a nice little research group at the Fritz Haber Institute in Berlin. And most of the results I show you today are still from this time. And I'll talk about laser cooling with deep UV, especially also highlighting a bit of the challenges that we faced. And motivated was this by the fact when I dealt with calcium fluoride at Imperial before I moved to Berlin is we always struggled to get more molecules. You've already seen this in the previous talks. We want to have more molecules. We want to have higher densities. So why is the density of molecular modes so low compared to atomic modes? I think we've seen already that this is due to inefficient sources. So compared to atoms, we have to deal with some chemistry. We are usually until now, where only radicals have been cooled. So we have an unpaired spin. This again lowers our reaction efficiency to give us just a lower number of molecules that we prepare in our source. Typically have pulse sources, so we can't really accumulate many molecules over a long time. We only load a single shot into a mod. The scattering rate is very low, so that leads to very low slowing distance. We are far away from the source. This lowers our density again. And the low scattering rate also then means that, that our capture velocity of the mod is very small. And so we know already that the number we capture in the mod scales dramatically with the capture velocity. And so finding a way to increase this capture velocity is a really nice way to improve this number that we can get. Also, there is no easy Zeeman slower. I hope Mirko will show us that there is progress towards implementing a Zeeman slower, but this also prevents us to accumulate molecules, and even worse, it leads to this weird effect like Tom already mentioned, is molecular pluming, that when you actually slow them at this really long distances, that most of the molecules will actually miss your mod capture volume. So hopefully by the end I can convince you it's not only that any new molecule brings new opportunities, and then if we investigate these kind of alkaline earth-like deeply bound stable molecules like aluminum monofluoride and aluminum chloride, it offers many new cool opportunities. So when I started, we basically just made a big list of molecules that look kind of promising. And a kind of nice way to plot it, I thought, was to the velocity, so to get the maximum peak acceleration as a function of the velocity removed for a single laser. So this axis gives you an idea how good the Frank-Condon factor is, and this axis gives you an idea what kind of the capture velocity is that we can expect in the mode, and also how long the slowing distance is. So you can see there's one that peaks out here is ALF. Also aluminum chloride and magnesium fluoride look very promising. So, but then if you look at the transition frequencies, you immediately see, okay, it's in the deep UV at 2 to 8 nanometers. So when I talk to people about it, they say, hands off, don't even bother, it's too hard. And I can report it's very hard. But yeah, we are working on it. Also means that I don't have a huge competition, and I have my own little niche where I can develop these new laser systems, develop new techniques, and not too many groups are actually starting in this kind of area now. But we have a nice little community, and I think we actually talk a lot and actually bring it forward. So especially for young PIs, it's very nice to have this little niche. When we started this, we had 4 big pillars. So we need to check if we can actually produce these molecules very well with a high density. I had to do a lot of spectroscopy. Because of these deep UV lasers, there weren't many deep UV lasers available, so there's not much spectroscopy that was known. This then allowed us to actually come up with a cycling and a cooling scheme, test it if it actually works, and now we are just implementing the slowing MOT and actually develop these deep UV lasers to a whole new level to make them more stable with higher output powers. All these are geared up towards maximize the number of molecules in the MOT and also maximize the density. Just meet aluminum monofluoride. It's maybe a bit more boring because it's a singlet sigma molecule and a singlet pi, but it offers this beautiful metastable state in between that we know and we love from the alkaline Earth atoms. So you can in principle devise a simple narrow line cooling scheme, and also use this extra triplet state for trap accumulation, resetting your photon clock, let the molecules rejoin the MOT and so on, and many cool advantages of using it. It might be a bit scary because there could be a very large fraction of you, or a very large leakage rate from this optical cycle here. So we had to measure this, measure all the optical cycling leaks, and then in the end it turns out it's actually negligible. What you also see is that the triplet transition here is also very diagonal, so very good Frank-Condon factors, and also easily accessible with a double TISAF laser. And when you then put all these together, very strong UV transition with a very big photon, you actually see that the slowing distance to slow the molecules down from 200 meters per second is only about 1 centimeter. So caveat is you need high power DPV lasers. Okay, we can deal with it, it's just technology, isn't it? So maybe I'll give you a quick overview how we produce this thing. So recently we put some effort in to actually make a CW beam of ALF because it's so deeply bound, it's so strong, this bond, that actually you can do and use your chemistry to your advantage here. So you heat up some AL3 powder, you wrap it in some aluminum foil, and out comes only ALF. It's really magical. There's no other reaction path. It's really the most stable constituent. This way, you can now measure the ALF partial pressure in the vacuum chamber with just a normal pressure gauge because you can produce millibars of it. So this is kind of the vapor pressure we see, or the molecules per second that you can produce at about just below the melting point. And you see it's many orders of magnitude more than we can produce in a pulse buffer gas beam. We developed this beautiful cryo-compatible oven because obviously it's a hot source, a thermal source, so we want to cool it down to compress the rotational state distribution. It only puts about 5 watts onto our cryocooler. So this is what we call a mega scan. We scan 2 terahertz in the deep UV to actually measure now the rotational state distribution of this hot source. And you see we actually see about 10 to the 16 molecules per stereo per second coming out. And now it's just, even in a single quantum state, it's already a pretty decent flux. But now we still want to cool it in a buffer gas cell. Even more amazingly, you can build a dispenser. So very similar to a normal alkaline MOT. And the very surprising fact is you can do it around the corner. So this means that the ALF molecules actually thermalize with the walls. They collide with the walls, and we can still see good signal here orthogonal to it. So it's such a stable molecule that it actually thermalizes with your vacuum chamber walls. We also built a couple of cryogenic buffer gas beams. And there we also wanted to understand the chemistry a bit better, just to maximize the source output. What you see here is actually the aluminum beam, calcium beam, and YB beam. And what happens when we add some NF3. And then you see with aluminum, in the case of ALF, when we add actually NF3, in the case of the aluminum beam, when we add NF3, most of it disappears. And if we then measure the flux of the ALF molecule, it actually fills this gap nicely. So we know it only again reacts to ALF. For calcium and ytterbium, this is different. And because it's a radical, the reaction efficiencies are much lower. And when we summarize it all, we see that we can produce it even in a pulse buffer gas beam with over an order of magnitude higher intensities. Just quickly, we did a lot of spectroscopy. I won't dig into the details there, but we had to figure out some very new loss rates from the optical cycle. This is 2-photon ionization. It's very important here because we are operating in the deep UV. We have to figure out if there are polarization dark states. Is there MOT even possible? And because we are now operating in a singlet pi here, the lambda doubling is very small. So this can actually lead to even small stray electric field can actually break your parity selection rules and then lead to large losses. So what you see here is before we actually had a deep UV laser, we just studied the triplet state first. So here you see just a normal PQ and R branch by exciting the molecule here to the triplet pi1 state, ionizing it with an excimer laser, And by scanning this excitation laser, we can nicely transfer molecules now up into the triplet state. Then we bought our first double TISAF laser. Then we actually replaced this pulse laser with a CW laser and immediately could resolve the hyperfine structure in the triplet pi state for the first time. And then we could even zoom in further and drive lambda doublet transitions in the triplet pi manifold and actually determine the hyperfine structure with kilohertz accuracy. And that allowed us now to really establish ALF as one of the best characterized diatomic molecules, and it's now being used to actually benchmark quantum chemistry calculations as well. There's many more spectra, but I promise you that's the only thing I'm going to show you. So this gave us confidence that we can invest now in these deep UV laser systems and that we can actually build and implement an optical cycling scheme. And compared to the other kind of calcium fluoride, strontium fluoride molecules, in this case, all Q lines are rotationally closed. And we can use the R and the P lines for optical pumping to actually enhance the population now in this J equals 1 state even. So you're not limited to a single transition anymore. You can have any Q line you want and actually use the other lines to even enhance your signal in the J equals 1. We also measured different quantum factors, and we can nicely scatter about 10,000 photons with only a single repump. Then a quick note about the hyperfine structure. Aluminium has a spin of 5 halves, so that leads to this splitting of this J equals 1 state into this triplet here. And then we've got the fluorine spin that then splits each of these F1 states into 2 again. And so we have 6 states here with a total of 36 Zeeman sublevels. Ground state is not resolved. It's about only 12 megahertz. That's important. Maybe remember that. The excited state, it's about 6 gamma. And if you scan over your Q branch, you can actually see that it's partially resolved here on the Q1, which is this line here. And then when you go to higher Q lines, the hyperfine structure actually collapses. A nice thing about this is, because we have a strong transition with a large hyperfine structure in the excited state, we have a natural white light slower. So it corresponds to about 100 meters per second. So we don't even need to add sidebands. Ground state is not resolved. No sidebands needed either. But obviously there are dark states we need to take care of. And the simulation here shows that even if we don't polarization modulate, we can still scatter at a high rate. And this is just because the aluminum nuclear spin actually remixes our dark M levels. And then if we start to polarization modulate, we even reach the rate equation limit showed in the dashed line here. So when we then tried, okay, the simplest way to show some cycling is just that you now compare your R line, for example, where we know exactly we scatter 2.5 photons to a Q line. And when we do this, you see there's a massive enhancement. So please note, we also used about 100 milliwatts of deep UV light here for the R line and the Q line. So same laser power. And you see this massive enhancement. And immediately shows you that the cycling actually works at a really nice high rate. Single laser beam, 3 millimeters. 100 milliwatts, no polarization modulation, no sidebands. We can also crank up the power, model it, then the details of the laser beam come into place. So it doesn't fit perfectly because it's not, the beams in the deep UV are not like beautiful, nice Gaussian beams. There are no fibers, right? So, but even accounting for that, it's a pretty good match. And we can reach this limit when we pump into the V equals 1. So from this, we deduced that even without polarization modulation, we scatter about 15 photons per microsecond, and we need to scatter about 2,500 to slow the molecular beam down. So it should only take 130 microseconds or so. Next step is to really measure the force you exert onto the molecules by deflecting the molecular beam, is what you see here. We added here this additional second deep UV laser system to repump, because when you have this really strong transition with a very diagonal Frank quantum factor, actually it becomes really hard to repump efficiently. So you then also need a very high intensity. And to test this, we actually see here that the integrated signal here is the same for both curves. And so that means that the repump works well, and we can actually repump efficiently as well. Once you have a push beam, you can also retroreflect and put a wave plate in, and then blue detune your laser, and then see that the subdoppler cooling works as well. We haven't extracted the temperature yet, and it looks like that it's very sensitive to high power deep UV lasers through your optics. They are not very happy, especially in the vacuum window. So they actually start to rotate your polarization, and you probably need to tone down the intensity a bit and do a multi-pass setup here to make it more efficient. Anyway, we were very happy to see that it works, that we also can use sub-Doppler cooling. We don't only rely on narrow line cooling, which I'll show you will be a bit challenging. To investigate narrow line cooling possibilities, we measured the lifetime of the triplet pi states. And if anyone has ever measured lifetimes in the millisecond range, they know how difficult that is and how annoying it is and how many months it can take. But in the end, we managed to measure it in a very cool way, I think, which is ratios of ratios between different pi states, and have different lifetimes. And so what we realized immediately is 2 milliseconds, definitely not a good lifetime to do narrow line cooling. So we need to effectively broaden it by coupling now these pi states back to the singular pi state, and do it in a way that we don't change parity. So this is what a preliminary kind of brute force small kind of experiment we did, is to excite the molecules now not with a CW laser but with a pulsed dye amplifier. This is the ground state population here measured with fluorescence, and when we apply the PDA, it drills a hole in it. This is the triplet population now, and then we pump it back by scanning a dye laser at 597 nanometers, and then we see that some of the molecules make it back, and we see it's only about 1,000 times smaller the population that comes back. So you need a crazy amount of power. We estimate to about 5 watts focused in a small spot, and an interaction time here of about 50 microseconds to actually make this a viable route. Next step, slowing. Again, because it's a very simple molecule and a simple structure, you just see if a Zeeman slower works, and you just need about 3 centimeter long fridge magnets, then orthogonal to your velocity in your laser beam. And then obviously there's a dark state again, so you need the polarization modulate, but it actually looks very promising to be a very efficient slower. Like I said earlier, the alternative is just to use this natural white light slower if it really doesn't work. But this immediately opens this whole possibility now to accumulate many molecules over many pulses, especially when you have a very nice CW beam. Next step is then trapping and cooling at the MOT. So like I said, we have 72 level DC MOT plus 2 repumps. So we use 4 UV lasers in total. The last one was just commissioned over the summer. We can reach up to 700 milliwatts at the moment, and we have a dedicated European network now to develop these lasers further to hopefully push it above 1 watt, but also in a stable way. Then, because it's a strong transition, we need a very high magnetic field gradient. So this is a picture of the coil setup that we have, that we can still allows us to switch the coils quickly, do it in vacuum, and produce gradients of up to 500 gauss per centimeter. To test this whole setup, to test the lasers work, and you can actually make a MOT of these using these nasty deep UV lasers. We made a cadmium MOT, so we can change between cadmium and ALF within about 3-4 hours by just tuning the lasers from 2 to 7.5 to about 2 to 9, so that doesn't take too long. We turn our targets to a cadmium target, and then just make a MOT like this. In the past, cadmium MOTs were always limited because of 2-photon ionization, and it's a lossy MOT. So, and I just highly advertise, if you ever have a lossy MOT or a lossy atom you want to make a MOT of, just use a buffer gas beam, because they load so quickly and you can reach incredible densities. And so what we did with this is also test an accumulation scheme, which is shown here. So if we ablate at 20 hertz, looks a bit funky because we want to prevent 2-photon ionization after each loading pulse. And then the next one comes, we ramp the intensity back up, and now you see that actually we can easily accumulate multiple pulses. Cadmium is not only good as our little dummy atom, but we can also measure isotope shifts very precisely, which is kind of a fashionable topic at the moment. And it turns out to be an extremely good candidate because it has 6 even isotopes with very high natural abundance. It's very close to this magic number. So it has a small standard model background, and we can also extract precise charge radius differences and then test actually new atomic structure calculations with that. So we got a bit sidetracked, teamed up also with Kurt Gable, and to measure all these transitions and all these isotope shifts, and actually put some kink plots up. To our surprise, when we measured the hyperfine structure of the fermionic isotopes, we saw this really strong quantum interference effect. So this is the extracted lifetime, or the line width, and the extracted hyperfine structure as a function of the polarization angle, or the angle between the polarization and the detector. So you get this really strong quantum interference in the laser-induced fluorescence, and that was a bit surprising, but it's not maybe too surprising because that was well known already. In the end, you can get rid of it if you just fit the right model that includes this quantum interference effect, or you just measure at the magic angle. So we took kind of the scenic route towards quantum degeneracy, which is we did a lot of spectroscopy, which is a lot of fun. I showed you that we can really produce ALF in massive quantities. We reached a really high cycling rate. It's an excellent candidate to reach really high densities. And when you reach these high densities, there are no reactions, because the bimolecular reaction channel, ALF plus ALF, is just forbidden. It's endothermic. And narrow line cooling is challenging, but it seems feasible. And in general, these triplet states are just a beautiful extra kind of handle to do beautiful new things. And I think one of the maybe underestimated ones is that when we excite these molecules to the triplet state, they suddenly have a magnetic moment, so they're trapped in the MOT fields, and so they can just decay back and rejoin the next pulse or the next kind of cycling in the MOT. UV lasers are a nice tool. Once you get them up and running and you can actually know how to handle them, they offer incredible signal to noise because you have these strong transitions. They offer really large accelerations, very high capture velocities, and there are many more applications beyond laser cooling for these UV lasers. So because we're such a little niche kind of area at the moment, we can actually explore many new things that actually go far beyond laser cooling. Also, we continue with cadmium a bit to push these kink plot measurements to the kilohertz range. And cadmium hasn't been laser cooled that much. No one has made a BC yet or studied any of the collisional properties. But it also has really nice properties for quantum information and simulation, especially because when you get it going to a lattice and you can actually get this super high resolution with the deep UV lasers, it can also be a very nice system. Let me just thank the growing ALF family. So recently, like I said, moved to Imperial. Still have a very strong collaboration between the two groups at the moment, and please reach out if you want to join our family. Thank you very much, and I'm happy to answer any questions.
Thanks, Stefan, for the great talk. So, floor is open for questions.
Yeah, so with the super efficient production and the strong cooling, I'm wondering if it's in principle possible to skip cryogenics.
Yeah, that's the dream, absolutely, yeah. So the dream was always to make a dispenser MOT, right, without any cooling. But I think it's already so efficient that probably just a cheap cryocooler, maybe, just with liquid nitrogen is probably enough to enhance it. The signal at low J is enough that it's a reasonable, good alternative.
Well, I'm gonna say the opposite. Why skip the cryogenics? The cryogenic button gets cooling. That's the key, right?
It makes it.
No need to skip the cryogenics.
Yeah, it makes it cheaper, more portable. If you, it's just. The UV lasers that so. I mean. No, I mean the new UV lasers we're building now, right? They fit on. They go now in a 19-inch rack basically, so it's kind of this volume. So they're not like massive kind of beasts anymore.
I have a question,
Yeah?
actually. What would you say is the outlook towards these UV lasers becoming sort of standard tools we can buy for not very high price?
So in this is exactly what we wanted to address, right? At the moment, one of these systems is basically, you know, like the equivalent of a fancy Aston Martin, right? And we just want to bring it down to a nice family car, right?
Is there anything else
So-
that is not a fancy Aston Martin?
No, that's what we are. That's why we teamed up with industry now and have actually a new, a new project with a European collaboration with industry. There's also Menlo involved to actually then take this over and make it a really nice commercial product. That's it depends on the power you want, right? If you just want low power versions, they will be available after this. So we teamed up with Vexlum, so a Vexel company, to integrate the first doubling stage into the fundamental, and then with Agile Optic, who is a spin-off from the PTB in Germany, to design stable new UV cavities, and then with Exma Optics to actually design the optics specifically for the deep UV range. So give us 4 or 5 years, and I think they will be nice, compact, and cheap, on the order of 40 to 50K. That's what we're aiming for.
I was interested, Stefan, about the window degradation. We see the same thing. Do you have an idea of timescale of that?
Yeah, well, it's totally power dependent, right? So the higher you go, the faster it happens. But what we're thinking now is actually just continuously rotating it, so you never actually hit a single spot. So, but I think it depends on the cleanliness of your vacuum chamber too. It's not only the substrate, right? So in the end, it can be on the order of 10 minutes or a day.
John, I have a question. I just answered it with that. It's a surface issue.
Yeah.
I was not sure if I fully understood your comment about the radicals, and you said they have an unpaired spin. So do you say the unpaired spin is the problem, or the fact that it's a radical and therefore doing a different chemistry?
Well, I think it's just that it's a radical, it's a different chemistry, and it's related to somehow having a free electron that's not paired up. And we see that from the measurements we did, but also from like ab initio chemistry, that the reaction pathways is actually very favorable towards producing calcium fluoride 2, for example. Whereas with ALF, you only produce ALF.
Say another question in the back.
Simple question. What rate do you use?
228 nanometers.
What certain styles doing Victor spectroscopy?
Yeah, exactly.
NO, the initial laser is somewhat similar.
No, actually, we also made a buffer gas beam of NO exactly for that purpose, right?
When they go in, they suit up with all kinds of stuff. They put stuff in their head, hoods and goggles. Do you do the same thing?
Yeah, you just need to work in a... Actually, we all use totally sealed cavities now. So they're all sealed. You never open them. They're all adjustable from the outside. That's a key issue. And cleanliness in your lab is definitely a good thing, yes. But if you have to open your UV cavity, you need to gear up. Yeah.
So, I don't quite understand the energy structure of the module, but to extend, if you have this 72 or 50 or 36 ground states there, I mean, while you are, is there a problem that you start to slowly mix to some ground state that is no longer?
No, the cool thing about this is, for example, that we can address all the same states in the excited state as well, right? The hyperfine structure is not massive, so they're all coupled to their equal counterpart in the excited state. And then in the ground state, we are lucky enough, compared to thallium fluoride, that the hyperfine structure is not tiny, but the aluminum nuclear spin splits it just enough that we can still cycle efficiently.
One last question.
Great talk. I wonder, the use of a buffer gas, will that affect your ultimate goal of making it easy? How's that going to feel like? Will it affect the pressure?
I think we always get this question, right, about what do you do with the helium, right? And does it prevent anything? At the moment, when we, for example, look at the cadmium lifetime or any other lifetime, it's never been an issue. You can put a shutter in, you add differential pumping, and in the end, you could even displace your molecules into a different chamber that has a much better background pressure.
Okay, let's thank
Okay.
Stefan